Hey guys, it's CS Wave, back with another video. I haven't made a video in about a year, and with the new year, I'm gonna try and upload more regularly. Hopefully, about like once a week or so. It's like a programming problem or a contest programming problem or something like that. Um, so yeah. Anyways, today we're gonna be going over the deepest node. It's a problem asked by Adobe. It's a pretty straightforward problem, but can sometimes trip people up if they haven't done a problem like this in a while. So the problem is, given a binary tree, write a method to find and return its deepest node, return null for an empty tree. So given this example, it would obviously return 9 since it's the deepest node in this tree, and looking at this example, you would return 4. So by deepest, the problem means the lowest level node and to the rightmost node. So like if you were to map out the tree into an array, it'd be the last index that isn't empty of that array, if that makes sense. You don't just want um, like if you were looking at the problem, you might start off by doing like thinking of a recursive way to do it, maybe like an in-order traversal. And in that case, you would get something like 7, which isn't the right answer, obviously. So yeah, looking at this problem, you want to recognize that it is a level order traversal problem, which requires BFS generally. It's the easiest way to do it, using some sort of a queue structure to hold your in-level sort or streamline, I guess. And yeah, I would definitely do this iteratively. Doing it recursively would be very difficult because you have to keep the state of the current path, the current like in order level that you're on, and stuff like that. So using a queue is generally the way to go for this problem, I would say. Um, so yeah, starting off with this problem, I would probably check for just the input being correct. So if root's equal to null, we'll just return null. And then we want to create our queue structure. I'm using Java. You could use whatever you want, but in Java, probably use the queue as a linked list. Since queue is an interface, you can actually create an instance of a queue, create an instance of a linked list. And with this, the add and remove functions act just like a queue, as in when you add something, it puts it to the back of the list. When you remove something, it removes it from the front of the list in that sort of way. So in the beginning, we will probably add our root to the queue, since we're going to, with this queue, just constantly remove from the queue and add the children of the node that we just removed back into the queue until we hit the last node. So I could say, while the queue is not empty, we're going to keep going in this while loop and removing from the queue. I should probably declare this outside. The create tree node that will return as our current node. We'll set this to null for now. So let's say cur equals q.remove, since we want to remove from the queue, and then if cur dot left does not equal null, since we don't want to add null to the queue, then we'll add that to the queue. And then the same for right. If it's not null, then we'll add that to the queue as well. Let's change this to right. And then at the end, we'll just return cur, since it would be the last item, the last node, the level order traversal. So for example, looking at the example here, you first add 1 to the queue originally, remove it, add 2 and 3 to the queue, so now the queue is 2, 3. Then we remove 2 since it's at the front, and add 4, 5, so now it's 3, 4, 5. Then remove 3, add 6, 7, so now it's 4, 5, 6, 7, etc. You remove 4, 8, 9. And then you end up with 9 at the end of the queue, and then you would return that. So thinking of space and time complexity, this would be O of n times, since you're visiting every node once, right? And for space, we would be looking at also O of n, since, well, at the most in the queue, you're going to have n divided by 2 nodes, right? Since the lowest level possible would be n divided by 2, which rounds up to O of n. So yeah, let's see if this runs. I might have made a mistake somewhere. Oh, cool. So yes, it works, and we could look at the complexity and Okay, we get runtime O of n space O of n, and yeah, that's pretty much it. So yeah, just to remember, BFS you usually use a queue, storing the nodes as you go along, and that's pretty it. It's a pretty simple problem. Categorize it as like a warm-up problem, maybe like a LeetCode easy sort of equivalent. Um, so yeah, that's it. Thanks for watching, and hopefully I make another video.